It's a pleasure to be here, and I hope you are ready for another course, okay, in this intense school. And my intention here will be talking about what is called on-shell methods, okay, and devoted a little bit to effective field theories, okay. As far as the course goes, you have been taught to effective field theories in the way that it comes from Lagrangian, that is described as a function of fields and derivatives of fields, okay? But we know at the end of the day, we want to calculate amplitudes because this is the thing we relate with physics, okay? When we square the amplitude, we get probabilities, okay? And this is a long path we have to take, and we learn how to take it, and you're learning how to take it, because that's the way to get theories that we like so much, Lorentz invariant, like causal theories, okay, and this is the path we learn. But it has been for already a lot of years that people try to develop other methods in which you start with the amplitudes, okay? You don't go to all this long path, okay, to Lagrangian, fields, all this thing, and back after that to amplitudes, okay? So you can start with the amplitudes and your building blocks of your theory are really the amplitudes themselves, okay? And this is the path I want to explain to you, okay? So let me review a little bit what I'll try to do. Okay, so this is the title of the course will be the amplitude approach to effective field theories, okay? And by the amplitude approach, I mean also what is known by the on-shell method, okay? And there are many reviews on these methods, okay? Let me probably put two here for if you want to know more the details of these methods, okay? I'll try to tell you that they are impressive methods, okay? It allows to understand things that you cannot understand from the Feynman approach, okay? So this will be my main motivation. Okay, so if you want to know more, there is a Lance-Dixon review that I put here, the number, and there is another, there are many of them, okay? So I am only selecting a couple of them, and this is Elbang, Huang, review that is and now because I need to fix conventions, and conventions, as you know, are different from places to places, I will follow my own convention, of course. And you can find them if you want more details in this in this paper of mine. Okay. So now the outline of the talk will mostly be two parts, okay? The first part is to introduce the method, on-shell methods, and at the tree level, okay? We will always consider weakly coupled theories, okay? So we'll start with tree level, and after that we'll try to see how we can do loops, okay? And I'll try to get to a one loop process, okay? How we renormalize the theories, okay? So we'll have to define now alternative way of defining the effective field theory will be via on-shell amplitudes. Okay, and for that we will need a little bit, this is the first mountain, and this is why not many people get into this amplitude on-shell method, because there is a small mountain you have to cross, okay? Depends how you are good, how you might develop the Lorentz group, you know more or less, but this is what is called the spin or realistic formalism. You get a knowledge of this, okay, when you get, you understand this formalism, okay, nirvana is in front of you, okay, everything looks clear, a lot of good thing, and I hope you can get excited to see how you can get the amplitude in a very simple way, okay? Okay, so this will be the starting point. After that, we will define what I say called the building block amplitude. And from that, how to get to higher point amplitudes and discuss the factorization. Okay, and the second part is going to the, as I said, this would be tree level, it's going to renormalization. A kind of alternative to what Rodrigo is showing to you. Okay, I mean, at the end of the day, the results must be the same, and are the same, of course, but these are done in a different way. Okay, renormalization of the EFTs, and I'll try to get into the RG's renormalization group equation of Wilson coefficients. Okay, via these on-shell methods. And the idea is to get what I said. With this method, you see something that you don't see, or you don't see clearly into a Feynman approach, and we will see new kind of selection rules. A lot of new selection rules you were not expecting, and you will see sometimes what I call natural zeros. So these are trying to explain some result that sometimes you calculate one loop. It doesn't look like it should be zero. There is no symmetry argument why it should be zero, but now you get zero. Okay, it has been a mystery for time, but you can understand through this way of calculating things. Okay, so I hope I can get to this point. Okay. Okay, so let me start. Okay, so what is the idea of defining your effective field theory via on-shell amplitudes? Okay, so it says replacing what you call your building blocks. Okay, what you have done so far is you have a Lagrangian. So Lagrangian is defined as by the terms of the Lagrangian that are operators in the quantum field theory. Okay, in some sense the I like to call it building blocks. Your building blocks so far has been these operators, okay, or terms in your Lagrangian, okay, phi to the fourth term, d phi square, okay, all these things you have seen so many, okay, of them, which you obtain by expanding around some cutoff in effective field theory, okay. And as I said, this is defined, usually are defined as a function of fields. And derivatives you have done so far, okay? With all the good things and the bad things, okay? For example, you have learned there is a lot of redundancies because you can redefine your fields. There is a lot of redundancies because you have to introduce gauge field, a mu, that you have to say, eliminate these extra redundancies to go to the physical states of two polarization by introducing gauge invariance. Okay, so you see here all kind of pain, okay, that you have when you do this approach, because you have to talk about or you have to describe your theory with a lot of unphysical things. Okay, at the end of the day, what is physical will be your states. Okay, and usually you have, there's a clash. Okay, between you start with a gauge boson, A mu has 4 components, and your state are 2. Okay, and this clash you have to solve it by doing manipulation, that is a gauge, either redefinition or imposing by themselves, that is redundancies to be cancelled. Okay, what is the idea of gauge, the gauge invariance? Okay, gauge transformations. Okay, so now instead of that, I'm saying this is the point is to talk about amplitude for the beginning. Okay, so even instead of starting with this operator, we will start with amplitudes that will define your theory. Okay, and now again, this is the big difference. This is defined it. Okay. That this one is defined as a function of your physical state. I usually define it as a, okay, something that is an eigenstate of momenta, and if they are massless, can be also helicity or, I don't know, charge or other quantum numbers. Okay. And this is the simplification. These are really the physical states, and not without redundancies. Okay. Now a little bit of. So this will be the main idea, okay? So I have to tell you, I have to rebuild in some sense the standard model for you, okay? I hope it will be easier, okay? Because in the standard model, you build it like here, okay? You do your Taylor expansion, the first terms of dimension 2 or 4 are the ones you learn of the standard model, okay? Here I have to tell you what are these building blocks, these pieces that define your standard model, okay? And later on, we will see you can create higher point amplitudes, okay, by using the rule of, I mean, there are different ways to do it, but I'll show you a way to do it in a simple way, okay? Not complete, but at least simple. Now, the gain, I was saying, okay, there are 3 examples I put you here to motivate, okay? Let me say the motivation, I already explained it here many times. Okay, it's just to see examples, for example, okay, we have discussed many times this theory with a scalar and derivatives. And you know, you write from the beginning, you write this term, and you ask yourself, it looks like there is an interaction with derivatives when you go to Feynman rules at p squared, at order p squared. And it could be also that there are more terms, okay? But you know, when you're learning, be careful, because you can redefine, you have to use your power redefinition to see that you can redefine away things, okay? And it's true, okay? You can use these things, but a priori it's not clear when you see the Lagrangian or you write your terms, okay? Your Lorentz invariant terms in the list of your Lagrangian, that all of them are going to give you 0, or not, or going to give you redundancies. When you go to amplitudes, of course, you define what is you are interested. I am interested in force scalar scattering. Okay. Okay, and so momentum, P1, P2, P3, P4. Okay, I'm going to take the limit massless. Okay, these are going to be important at some point, but I can, if they are massless scalars, thinking about pions, for example. Okay. Now your amplitude, A, will be proportional. You are looking for something that is proportional to momentum squared. Okay. So it has to be proportional to one of the Mandelstam variables. I can define it here for, okay, let me say something. I start already here saying that I will say it. I will use it all the time. Usually I will use the momentum always of the state incoming. Okay, when I talk about amplitudes, okay, the momentum of the momentum will be all incoming. Okay, this looks like unphysical to you because probably, okay, okay, 2 must go, okay, 2 must enter a momentum, 2 must go outside in the physical process. Okay, but right now, okay, let me extrapolate to mathematically to consider the possibility, okay, that this, okay, this is not, the momentum in some sense here is having a different sign, okay. When I write the amplitude, let me write it in with this possibility. When I go to physical states, I have to go to the process where the energy is positive and blah, 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 okay? So let me take it as amplitude at this level to also always considering, okay, so P3 will be the opposite sign, but okay, you can do it easily. Okay, the important point is that it has to be Lorentz invariant. It has to be written as this simplify my life. Otherwise, if I change the sign of these guys, I have to change the sign in T and U, as you know. So your amplitude has to be written as a function of this at order P squared Lorentz invariant variables, the Mandelstam variables, okay? So will have to be proportional to S, to T or U. But now you realize all because of the same states, okay, you have what is called crossing symmetry. It's something you can use, you have to use when you do amplitudes, okay, that, so you interchange these particles, the amplitude should be the same, or these particles, the amplitude should be the same. So if I do the interchange of P1 to P2, okay, or the P1 to P3, P1 to P4, okay, the amplitude should be the same, okay? So this means S, if I do the exchange of T with U, the amplitude should be the same with S or with U and T with S, the amplitude should be the same. So it's clearly if I have to write something that is crossing invariant written as a function of Mandelstam variables, it only has to be proportional to S plus T plus U. That if the states are massless, S plus T plus U in an amplitude sum to 0, okay? In some sense, directly here, I try to build the amplitude, okay, as a function of Lorentz invariant, okay, using the cross symmetry, I see that this amplitude is 0, okay? If I want to go I want to add more terms, I can proceed the same way. So, for example, if I interested now at the Lagrangian level of theory what contains 4 derivatives and 4 fields, okay, now you have to build the Lagrangian and write all terms you are allowed, okay? And after that, calculate the amplitude, okay? In the amplitude level, I know how it goes the next term. The first term is 0, okay, coming from the first part, okay, and can add here the, I know that the second part will be a 4 derivatives. It will go like S squared or S times T or S times U. But again, crossing symmetry tells me that this is only, there will be some coefficient here, let me say A, order S squared, T squared, U squared. Okay, there is no more way to write this thing. So going directly to the amplitude, I know has to go, first term should be 0. Here you don't get any contribution. Second part, I don't have to go through all possible terms I am allowed with 4 derivatives and 4 fields, write the Feynman rules and get all the possibilities and get something like this, because I already know my Lorentz invariant, can start with my amplitude, okay, and say, okay, my amplitude should be proportional to this at order S squared to this thing, okay? And this is more or less the philosophy, okay? If you start with a theory like this, okay, okay, you can, this is dimension 6 operator, I put lambda square, and this is dimension 8 operator. So in some sense, the same way you expand and you say, oh, this is the dominant one, subdominant, because this is a higher dimension operator and so on, and you do your Taylor expansion in the Lagrangian, we will do the same here, okay? We will do some kind of Taylor expansion in the amplitude because I know this term will be some coefficient, 1 over lambda square, okay? And if I am interested with lambda goes very large, I can drop this term and the amplitude is 0, okay, and so on. So it's the same Taylor expansion that you do into the idea of effective field theory. There's a Taylor expansion that you do in your Lagrangian. It's also translated in effective field theory of amplitude by some kind of Taylor expansion, okay? Yes, the other terms you can derive like, yeah. You have to see the others and the end. You can write it with this. Okay, you say you could have terms like ST. Yes. The massless always S plus T plus, yes, you have to remember, yeah. These are massless theories. Okay, so yeah, there is a little bit, okay, probably I'm skipping a little bit the detail to see that there are more terms, but at the end of the day, those are reduced. Yes, sure. Sorry? It's tree level, yes, everything is tree level. Yeah, I'm assuming that there is an expansion parameter I can do. There are two expansion parameters, the one that you learn in effective field theory, that is your terms 1 over lambda, okay, energy over lambda. This is an expansion of effective field theory, and after that there is a weakly couple theory, so there is a loop expansion that you do. And you're learning how to do it from Rodrigo, from the Lagrangian point of view. We'll do it here. Now, there is another beautiful example I like to put to motivate the amplitude is, this is a classical example, is when you look at, let me go from something very simple, scalars, to something more complicated. The higher spin is the particle, the better you are, the simpler is doing is with amplitudes, you see. It's the opposite with quantum field theory. Quantum field theory of scalars are simple, but when you put fermions, it's complicated. The spin one is more complicated, because you have the gauge redundancies, you have fixing gauge, all this complication, and you go spin 2, okay, even more indices things. Here is the opposite, okay, for example, scattering. Okay, graviton scattering, we will calculate this thing, okay. This is a classical example. Now, if you do it through Feynman, you know what you have to do. First, you have to learn GR, or linearized gravity. You have to get the Feynman rules. Okay, you have all this thing, graviton, this thing, crossing. Calculate each of them, plug them back, and now you get a result, okay? Now, the result can be written, and we'll do it by amplitudes, in a very simple way, okay? When you select the helicity, because we are talking about physical states at the end, graviton are massless, so they have two degrees of freedom related with the helicity of the state, plus 2 and minus 2. Okay, so if you select this amplitude to have definite helicity like plus 2, minus 2, minus and plus, okay, this is the state 1, 2, 3, and 4. No. Now you will not understand what I'm going to write here, because my purpose is to, what I'm going to learn is to write that this is going to be, of course, proportional to G Newton. This, we already know it, but it's going to be written in a very simple and packed form. That is this one you see here. Now you will tell me, I don't understand what you're writing. Of course, this is the idea. This is the amplitude, okay? So after you go through the pain of a very long things to get the Lagrangian and like that, you get at the end, you see at the end of the day, and we'll do it through amplitude, but you can also do it here. You can pack it in a very simple way. You don't know what are these things in the numerator, I understand it, okay? These are simple things that we will define, okay? My purpose here is to motivate that there is a, it looks like there is a long path to go through the Lagrangian, but there is a short path, because you will learn this to do this when you cross the mountain of the spin or helicity formalism. When you cross this mountain, you will do this amplitude in 10 seconds. I'm not joking, okay? Okay, so this is the idea, okay? Yes. This is, yes, exactly. This is an amplitude for the particular helicity of these states. If you want to put plus to all, you get 0. Okay, if you put plus, and you do the calculation, you spend a month probably, and you get 0. Okay? Sorry? This is the only surviving amplitude, yes, yes, because even if you put 3 plus plus and 1 minus, it's also 0. Yeah. Yeah. Okay, here doesn't matter now because you don't know what is this, so doesn't matter in some sense. The motivation to me is that it's a really nicely packed formula that is very difficult, in fact, to see from here. It took the first guys that realized in gauge theories, it was an amazing thing that after summing diagrams, it was engaged, as I said, in gauge theories, they could pack it in a very simple term, okay? It's not supposed to be because it's true that you have poles in the T channel, S channel, U channel, that you can also see here. There is a pole in the S channel, T channel, U channel related with exchange of particles. But usually this is sum, this plus this plus this plus this. Okay, not clear. You have to factorize in something so simple. Okay, so this is the motivation to see that there is a taking this second row looks like the amplitudes show a simpler structure. Okay. Very good. We will come to this point. Yes. Okay. Yes. This is related kind of with my building blocks. It's also here. It's not clear. You see, at some point here, at some point this thing when you talk about, you start with you learn here how to do it, no? Because also when you go to quantum level, these operators start depending on the renormalization scale, things like that. Become complicated at the loop level, all these things, what is operator, what is not. Everything becomes more complicated, but you know how straightforward will go. You start with T level, I know what this thing means, okay, include loops, okay. So in some way, yes, I have to go proceeding in a similar way, okay. So the amplitude at the level here would be, okay, would be an amplitude that, okay, yeah, okay, I will explain it. Yeah. Of course, it will be, is exactly the same as going through Lagrangian. Okay, so this I would call, of course, you see, this I would call a 3-level amplitude. Okay, it's coming from, so it is true that I'm saying I have to go to certain things, I have to go, so the good thing of the Lagrangian is a very clear path to go. If you follow the path, you calculate everything. Here, as you will see, the path is not so clear, it's not so straightforward. If you tell me, I want to calculate something at 5 loops, I don't know how to do it. These on-shell methods. But people develop methods, okay, to get to it, okay? So there is some limitations here, okay? So what you learn is something solid in the sense you can calculate everything, but it takes a long path, okay? The mountain is higher through Lagrangian and going back to amplitudes, okay? Here the mountain, I hope is smaller because I have to learn about this spin-relicity formalism. Okay? Exactly. A good question. What are these guys here? No? Yes. These are the spin-relicity formalism. There's a motivation to show this that only the idea of it can be written in a simple way. I understand you don't understand this, but there's a motivation to learn this. Okay, what is this in denominator? Yes, this I have to answer you. Okay, the rest you can understand. The Newton and the STU are the Mandelstam variables, and they are poles, telling you they are poles in the 3 channels. Okay, as you expect also from Feynman. Okay, these are guys related with the elicities. Okay, we will see. Okay, so more or less I explained the idea. I hope you understand. Okay, so this is the equivalent of this is the basic thing. Okay, and the effective field theory idea I also put it in this example. Okay, in the same way you do an expansion in operators, 1 over lambda. Okay, we will do an expansion in these amplitudes. Okay, terms that go without lambda, terms that go like 1 over lambda or 1 over lambda squared, lambda cube, okay? And I'll treat it, and it's obvious my expansion, that is the same you do, of course, in, you know, it's the one really you are doing when you do the Lagrangian. Okay, and the Lagrangian is a derivative, of course, but at some point in the amplitude will be momentum. It's an expansion very clear already from the beginning, is momentum over over lambda. So your effective field theory works when the momentum over lambda is small, and these terms are a small perturbation, okay? Okay, so let me go to the, I'm going very slowly, of course, to this thing, okay? Yes. Will this work for? Loop amplitude, yes, this is what I was saying. The part we will do loop renormalization. We will do one loop, but there is when we go to loops, you have to be careful. There is no a clear algorithm as you learn quantum field theory. In quantum field theories, you know, okay, you get the formalism and you know how to calculate one loop to loop three loops. Okay, there's a process of which you've learned and you can calculate any loop. Okay. Here, there is not a clear path, but we will see how it goes. The problem is these guys are defined, okay, I didn't say it, but of course the states are on shell, are defined on shell. When you calculate loops, there are processes coming from the off-shellness of the particle, okay? And this is quantum physics, okay? Not only, okay, always you don't see the particle, so the particle is going off shell, and there, that contribution, of course, is going to be, you see, is a problem for me, okay? Because if I want to define things on shell, how am I going to do calculation where you have to go off shell, okay? So I have to elaborate on this thing. It will not be easy, but I will elaborate on these things, okay? I will tell you at one loop level is relatively easy, okay? But I don't know, two loops is already difficult in quantum field theory, okay? So you will agree with me, no? Yes, better? You think so? And I think better I start here. I am a person that I want to be in center. Okay. So now the spin or formalism, okay, this is the thing you have to get used to it, okay? And this is related with this angle bracket and square brackets, okay? That you see there, okay? This is the mountain to cross. And when you get used to it, because when you do quantum field theory, you cross a lot of mountains. You have to learn the Lorentz group, the P mu, how you rate invariance, how you rate Lagrangians, all these things, okay? So, and this is why you are familiar and happy to write theories, because you know how to do it after you're learning the techniques, okay? So here, okay, the idea is relatively simple, depends how well you know the Lorentz group. Okay, because usually the Lorentz group is defined by rotations that leaves the four momenta of the four vector invariant, okay? And those are, apart from demanding certain things more like positive, okay, different other condition, like the determinant has to be positive. I mean, apart from extra conditions, okay, I could say the group is mostly transformation that leave invariant the norm of the four momenta, okay? And this is the group SO13, okay? And you know the Lorentz transformation are usually defined by these guys, and we know the four vector transform, okay, with these matrices, okay, of determine the Lorentz group, okay? So this is the way you know, and you know the momenta, your amplitudes depend on this momenta, because you have an index Lorentz, you know you have to contract it to make it Lorentz invariant, you contract with the G mu, and this is the way you know the amplitudes will be always proportional to products of four momenta, because these are Lorentz invariant objects. Okay? Now, probably if you know it, already went through this on the books. You can go to this group, in any book of quantum field theory. This group locally is the same as the SL2C, okay? Has the same Lie algebra, okay? Same generators, 6 generators, and this is the group of 2 by 2 complex matrices. Of determinant 1. With the condition, you can see that there is classified by 6 parameters. Now, probably let me say something before getting to what I'm aiming. Yeah, sorry. I started with details. Okay, I'm aiming very simple thing. If you don't remember this thing of Lorentz, but you have to remember similar things in the rotation group, okay? Okay. Rotation group, similar thing, okay, is the orthogonal group that lives invariant the, okay, the transformation that lives invariant the norm of the 3 vector, okay, up to projecting, again, parity or things like that, okay. But this has a similar, locally similar to SU2 as you learn in quantum field, in quantum mechanics, okay. So these groups are locally equally, of course, globally as details that probably you already learn in quantum mechanics. I'm not interested now in this thing. And the idea, of course, is that you can write a rotation, okay, you can write a representation that is a 3, spin 3, okay. From here, SO3 is the fundamental representation of SU3, okay. It is the orthogonal matrices of 3 by 3, okay. That is the usual rotation of the 3's component of a space, okay. But you also know when you do quantum mechanics that the spin 1 representation, okay, you can get it from the fundamental, you can also get it from the fundamental of SU2, okay, where the fundamental of SU2 is the spinor, okay, you have the spinor and you have unitary matrix on the spinor, you have unitary matrix 2 by 2 complex unitary matrix of determinant 1, remember the S means the determinant 1. You can also get this spin 1 by doing products of simple spinor representation, okay, psi bar or psi, okay, you can get higher representation, okay, so spin 1 can come from a spin product of the spin 2, okay, so 2 times 2, okay, you get the spin 1, 3 plus 1, okay, so you know that 2 electrons, for example, can have a spin 1 or spin 0. So this is the idea, okay? I can look at here. This is what we do when we consider a group, or I can consider as a product of the representation, as I do with the rotation group. In quantum mechanics, the writing the spin 1 not like this, but like a product of a spin a half. So I say the spin 2, sorry, 2 components. This is a spin a half, sorry. I say spin 2. Okay, so here I have a spinor, this is 2 by 2, so I have here a spinor. This will be my spinor here. Okay, alpha goes to 1 to 2, and will transform by some matrix M. This will be the fundamental representation of this group, that these are the 2 by 2 complex matrices acting on spinor, is a representation of 2 components, okay? And I will be also interested in the complex conjugate, complex spinor. Now in the literature, we like to put it a different label. We write it like this. We put like psi with a bar and alpha and a dot in the top. I don't know, it's too exotic to you. I mean, write it as you like, okay? This is the way we like to write it. Okay, by the way, this is in component would be, sometimes I use matrix way of writing to simplify and not keeping the components. Sometimes I go to the component to make it clear. transformed with the complex conjugate matrix M. Okay, and sorry for these betas, and I don't know why people put these indices there, but that's the way. Okay, and now I can do the product. Okay, so I can get the spin 1 from the product of twos of spinors. I can get the same thing. I'm aiming for the same thing instead of transforming this way. Another way of understanding the transformation of a 4-vector under as a product of spinors. Okay, and the one I could consider the product representation would be this psi alpha dot. Okay, that we call up, that is a matrix because depend on two indices, P alpha dot. Okay, and this will play the role of my P. Okay. I don't know if you know all these things, probably. Most of you went through with care under the Lorentz group, you get all these things. Okay, the transformation of this P under Lorentz is P goes to M. I know how this guy transforms, of course, because it's made of product of spinors. I know how the spinor transform. I know how this thing transforms. I have to follow. And this is in matrix notation is this P goes to, this is a matrix depending on two indices, 2 by 2. This matrix goes to M, P, M, daga. Okay. This is the Lorentz transformation. Okay. And my point is, in some sense, to replace your amplitude. You write it. You like to write it as a function of your momenta. No, as I said, everybody knows how to do it. And Lorentz invariant products of momenta. Okay, in some sense. Okay, you have to. But I'm not going to write my amplitudes. I want to write it as a function of these guys here. Okay, and the first term, I would say, instead of using this P mu, I write it this P mu as a function. I'm going to replace the P mu. I will use this matrix representation here. Okay. I will show you in 2 seconds that this Lorentz transformation, or you can see, or I'll show you in 2 seconds that this Lorentz transformation indeed is doing what a Lorentz transformation is doing. Okay, it's a transformation that leaves invariant the P mu. Okay, this is the definition of the Lorentz group, plus something else that little details on the parities and the things, but this is the definition. Okay, the four momenta interval for momenta, or whatever you call it, is unchanged under the transformation. Okay, and now, so I want to replace with this guy, and this guy it can be written as sigma mu P mu is exactly as you do in quantum. It's exactly what you do in quantum. Doesn't work. Quantum mechanics when you want to do it. What is this guy? This guy is okay. These are matrices 2 by 2. Okay, and I have sigma 0 is the identity. Sigma I is the sigma Pauli. How to write it? Sigma Pauli. Pauli matrices. Okay, and you can write it this thing as a P. If you write it explicitly, this is P0 plus P3 as a function of the components of P mu, P1 plus I, P2, P1 minus I, P2, P0 minus P3. Okay. you can check that the determinant of this P is exactly P0 square. Okay, you do the determinant of this thing, P0 square minus P1 square minus P2 square minus P3 square is the for momenta square. Okay. And now you see that indeed this is a Lorentz transformation of the four momenta. Okay. If I look at the determinant, how to transform the determinant of P, I take the determinant here, and because these matrices are 2 by 2 matrices of determinant 1, I get the determinant of the product is the product of determinants, so the determinant of M is 1. I get that this is transformed to something that is 1, determinant of P, determinant of M dagger that is 1. So I get determinant of P goes to the determinant of P. Okay, so under Lorentz, the determinant does not change. Okay, so we already proved what we're looking at is that the is equivalent representation of this case here. Okay, Lorentz transformation is the guy that gave me this invariant. Okay, I wrote it in this matrix way. Okay, it's a product of spinors. Okay, and I found it that the transformation has to be this. And indeed, this gives me equivalent transformation that leaves invariant the four momentum, the norm of the four momenta. No? Okay. Okay. So the idea is, of course, it's equivalent. And now the question is, instead of going through Lagrangian to write it like this, P mu's, I will write it like to use these things, but still more simpler things. Okay. Right now I only, okay, I found an equivalent representation. Okay, these are the same thing. I have this representation as a function of these 4 by 4 matrices here. Okay, now my representation is a function, it goes like this, with this M being a 2 by 2 complex matrices. Okay, but it's equivalent. Okay, this has the same the algebra, and it gave me the same transformation of these four momenta. Okay, but written in this a little bit more priori complex way than the other. Okay. Now from now on, I consider massless states. This is something that that I have to admit that the on-shell methods are very simple for massless particles, and become a little bit more complicated when you go to massive particles. Okay. Now what we're going to do? So what we're going to do here is consider only massless states. Okay, massless particles. Okay. For high energy experiments, okay, you can neglect the mass, okay, and that's okay. You talk about the standard model, okay, you define the standard model with all particles are massless, okay. So in some sense, there will be correspondence between how you define your Lagrangian, the standard model, and my amplitudes. Because you start with a theory a priori, you write it as a function of massless state, okay. Now this is important because, of course, the determinant now will be 0. P mu is the mass square. The mass is 0 for everybody. Okay, so for any moment of any particle, we know that the determinant will always be 0. Okay, and now comes the second step. Okay, is to write these matrices that it was a product. We have to go back here, and we know you can write it as a product of two by 2 components. This matrix, because the determinant is 0, it has rank 1, I can write it as a product of 2 vectors. Okay, now I have to consider like 2 vectors. You can consider it as a, here. Probably I'll write it like probably write it like this, okay? Psi alpha, like, sorry to use the same notation, psi alpha dot, and now it's a product of two component vector, okay? You know, when you write something as a function of two component vector, a product component vector, the determinant is 0. Okay, so these are two component thing. Okay, that you multiply by it. Okay, so in some sense would be. Can I do it explicitly? Probably to be clear. Well, I probably okay. So since you write the lambda 1, lambda 2, and you write this lambda 1 bar, lambda 2 bar. Okay, this would be lambda 1, lambda 1 bar, lambda 2, lambda 1 bar, lambda 1, lambda 2 bar, lambda. Okay, sorry, or I missed something. I went too fast. Yes, here there is a 1 and there is a 2, 2. And this guarantees that the determinant of P is 0. Now, instead of I've talked about notation and like 1, 2, this is, okay, you saw things like this. Okay, and now I want to define what are these objects. This is, again, it's a notation is used, if you don't like it, change it, okay. The notation is used by people, by everybody, so everybody can understand. So instead of, we could be talking about these spinors, two component spinors, but people prefer it, by some reason will be clear later, because it's easy to write them. People prefer to use this notation of with this angle spinors and square spinor. Okay, so instead of writing like this, the P, okay, now the notation will be that the notation people use. Okay, if I have a particle of momenta P1, we will have this P1 matrix, okay, we don't talk anymore of P1 mu, P1 matrix, alpha, alpha dot, okay, and now we write it as the spinors, we write it like it's a particle 1, okay, every state we will put a number, okay, so its momentum P1 is the particle 1, it will be particle 2, particle 3, particle 4, this is where you saw this number. The 2 by 2, there are 4 particles, everybody is 1, 2, 3, 4, you have to label by this, okay. And now the P will be a product of these two spinors, okay, that one will be written like this, angle spinors, and what is corresponding to the complex conjugate of it will be written like a square spinor, okay? Sorry for this, looks like very much a lot of notation, but this is the way it is, okay? This is the mountain I told you have to cross because it's the way to change when you write the amplitudes, okay, instead of P mu, you have to change it to this. We're going to talk about this, will be the ingredients to write my amplitudes, this guy, the spinors, okay? Instead of the P mu, as I said, it's going to be these spinors. Okay, they carry some indices, okay, under the Lorentz group that I define in the SL2 complex, but that's okay. I will have to contract these indexes, and that's it, to get the Lorentz invariant, okay? So instead of having P mu, contracting with P mu, I'll have to talk about these guys, okay? There's a couple of steps more. Probably, I don't know if to stop here. Yeah, lambda 1, yeah, sorry, I went too fast to show. Yes? Yeah, I didn't put them.
Bars are with the dots.
No, this is the This is the first component of the, yeah, these are two spinors, no? Two components.
There's no dot on the other one?
Here? Yeah. No. Here, the alpha goes to 1 and 2, it's a spinor. I put it explicitly here. Yeah, I don't want to confuse you. Okay, this is a guy with two indices, okay? So I give you the two indices. So the two components, okay? Alpha to okay. Alpha goes 1 to 2, these are the two components. These are guys with two components. I put explicitly the two components of them. Okay, to write that this thing, to see that when it's a product of this thing, is always a determinant that is 0. So, yes. P, yeah, the P, sorry, sometimes I put the P is now a matrix, okay, has two indices. Yeah, come in, go back here, sorry. Okay, your P mu, you learn a lot and you spend time, but to know that this guy has 4 indices is a vector with with 1 index and 4 components, sorry. Too fast, okay. Okay, this guy is okay, you learn this, but now this P mu, and you write it like this, and you transform under Lorentz like this, with matrices that are 4 by 4. I change it, okay, as you do also sometimes in quantum mechanics to represent the same thing, okay? A P mu, a third component under the Lorentz group, but in a different way, in a matrix way, okay? As a product of a spinor representation, okay? I get this a product of a spinor representation of this group. Equivalent when you do quantum mechanics to write the spin 1 as a product of a spin half, okay? 2 component, spin a half, you do a product, you get a spin 1, okay? This is the same representation written in a different way, but the same as when you do a rotation of a 3 vector in the space, okay? It's a different, okay? It's equivalent thing we're doing here. If you're familiar with Lorentz group, this is okay. But if not, you go back to quantum. It's good to go back to quantum mechanics and remember that you can write the spin 1 as a product of spin a half. We are not doing more than that, okay? The group has the same structure that SU2, okay? And there the fundamental is a doublet, and I write all representation as a product of doublet, okay? Here I can write all representation as a product of this 4 component, 4 vector, but because I have the same algebra, the fundamental is a spinor, I can write also, okay? Because it's the same algebra, okay, the representation should be the same, but written in a different way. Okay, I understand this can be, for the first time, can be confusing that I can write it like this. Okay, so in a sense, your P mu, okay, using this notation, the P mu, you want to recover what is the P mu, with your mu here, okay, of a particle 1. This is, okay, you can see that this is exactly, okay, this is an exercise to see that this is exactly sigma mu. 1. Sigma mu, that is a matrix contracted among these spinors. Okay, this is probably. Sometimes this is not needed, okay, because the P mu, we're not going to build amplitudes with the P mu. This is the way you have done it. We're going to write amplitudes with these guys. These are going to be the guys for us now, the spinors. Okay, the amplitude will be written with the spinors. Sorry? Sorry, here? Here, yes. Yes, this guy is this guy. Ah, you mean that, yeah, there's some, okay, sorry, yes, sorry. Okay, what is this? Yes, yeah, probably. I anticipated this result. Yes, I anticipated probably this result because you don't know. Yeah, this is okay. This would be okay. What is this exactly? Sorry. Yes, what is this exactly? Probably anticipated this. This is a matrix, no? Sigma mu is the matrix there, 2 by 2, and now this is contracted with these guys. No, this is contracted. Yeah, probably let me probably skip this thing. I have it here, but probably let me skip it. Let me probably later. Yeah, sorry. Yes, sorry. You're right. Let me keep it for later. Yes, let me keep it for later. This is a contraction of the. This is a contraction with the spinors. Okay, let me keep it for later. Let me keep it for later. Yes. Yeah, sorry, it was not. Because I have not defined yet the contraction. Probably let me stop here, but the idea is to, it didn't get much far away. The idea is to get to amplitude that will be like this, okay? And my idea will be that instead of writing my amplitude as you do, depend on momenta, and momenta contracted, like P1 contracted by P2 and things like that, okay? I'm going to write the idea with my spinors, but I'll have to contract them with alpha, okay? I will tell you how to contract them. Okay, I can write it here, but okay, I have to contract them. Okay, I have to do Lorentz invariant amplitudes, but with these objects. Okay, this is the idea. And this will get to this contraction that we see here. Will be 1 and 2. Okay, that I have to define how to contract these two guys. Okay, to be Lorentz invariant. Okay. This thing, sorry here. This thing, you know how to do it. Okay, but well, here it's very easy. You only have to contact with epsilon, but let me introduce the next day. Okay. Okay, probably. Huh? Sorry? Fermion fields never, no. I will not never talk about fields. These are not, sorry. Yeah, that's a good question because when you see this thing, you get confused that you are talking about fermion fields. Fermion fields, okay, so this is a representation, a spinor representation, okay, that you can use also for fermion fields, okay? Now our fermion fields, and because, be careful because when you're fermion field, they are anti-commute, okay? This is a representation, this is a mathematical object, okay? I can use it for fields, I can use it for states, I can use it for anything. Okay, so, well, for states, no, because it's not unitary. But I can use it for whatever I want to study symmetries, how to transform objects, how they transform. The object, when it's quantum field theory, this becomes a spinor field. Okay, so this is a good comment because I write the same notation because I like to remember, oh, it's like a fermion field, transform like a fermion field, transform like a fermion field, but it's not a fermion field. Okay, so these guys are not going to anti-commute. Okay, when this fermion, you put an extra ingredient. Oh, I want them to commute. Okay, so no fields, so no representation. Sorry, you got a, yeah. I like to emphasize this thing because people get. Yeah. Yes. Exactly. I spent a lot of time something that you did in quantum mechanics. Probably you did in. Yes. Only this. And we are going to split this matrix in spinors. Okay, so you see the 2 by 2 is going to be even broken, okay, if you want, I don't know how to say it, okay, but decompose into spinors, and this is going to be the ingredient guy, the big guys. The spinors are these guys, okay, so first, the momenta is written like this, and now I'm going to talk about these guys themselves, isolated. I'm going to do some, because the PMO is very intuitively mathematically, but this spinor is not so intuitively. Okay, when I talk about this, you ask me, what is this mathematically? And you have to, okay, you have to use them because I'm not really losing a little bit of intuition. Yes, that's the way it goes. Okay.
We are doing it in two ways. One is to write it as tensor product of psi alpha and psi bar alpha dot, and then there's sigma, contacting sigma mu and p. Are these two definitions included or these are two completely different?
No, the one you have to compare is this one with this one. What you want to compare?
The last line here and the first line here.
Yes.
Both are representing a 4 vector in terms of 2 plus 2.
When I write it always as a product, okay, I mean, automatically you are creating a matrix. It's a product of a spinor, you have two indices, okay, so this is a matrix with 2 indices, so 2 by 2, because each index goes from, has to come.
Are these two definitions? The last line here and the first.
Oh, this P, sorry, this P is this, okay, sorry, yeah. This P is this P. This P is the same, yeah. My point was here, sorry. Sometimes, if you see a P without anything, it's a matrix, sorry. Okay, sometimes I use the matrix 2 by 2. If you want to put the, yeah, I drop the indexes, so otherwise we'll be boring alpha, alpha dot, alpha beta. Okay, you can do all the indices. Okay, these are matrices. M, 2 by 2, P, 2 by 2, M, 2 by 2 matrix.
Here, when you define the determinant, it's always zero. It's identical, no matter what P we take.
For massless, yeah. No, the determinant is here. I calculated here to you. Determinant is P mu. The determinant of this object, yeah, I can argue about how I got this. I thought I didn't want to do it. Okay, I only, yeah, decompose this guy, okay, that is a 2 by 2. Okay, decompose it like this, okay? Now, okay, I went here too fast to show you that later on I wanted to show that this is really the Lorentz, if I write it like this, where P mu appear, the Lorentz transformation of this object, this, okay, is going to give me, okay, it's going to be equivalent, to this point here, okay? The P mu, okay, Lorentz transformation is a P mu, is a transformation that leaves P mu invariant. Okay? This is what I wanted to show here, okay? That written in this way, okay? In some sense, this transformation is rotating P mu, okay? It's a transformation that changes P mu components, a rotation on P mu, Lorentz transformation of P mu, but leaving P mu invariant. Yeah, yes, at some point now here, P mu could be M squared, okay?
There it's always zero, even if it is transformed. Because the determinant of that matrix is zero.
Exactly, here imposes 0, and now I write it, I can write it as a product of two vectors, two spinors, okay? And this guarantees, here is a proof. If I write it as a function of two components, I have the determinant is 0.
Why do we use infinite mass?
I impose it. I'm going to treat states that are massless. It's a special case. Sorry, it's a special case, yes. I can write it as a function of these two columns, okay? This is only if the determinant is 0. If I want to go to theories where the determinant is not going to be 0, I will have to write it not as a function of these two guys, but more things, okay? Because as soon as I write a 2 by 2 as a product, tensorial product to vectors, okay, now becomes determinant. Going too slow. You can ask me any question. Yeah. This is what is probably the fact that we're going to. This is the difficulty. Okay, you're very used to do amplitudes with P mu. P mu for you is okay. You see it everywhere. Blah blah blah. Now we're going to talk about these spinors. Okay, and we are going to lose a little bit of intuition. Okay, because this is spinors, what it is. Okay, P mu, I know what it is, energy, and the others are the three momenta you learn in the school. Here, now, it's true. Okay, I'm going to lose a little bit of what exactly is going to be this object, okay, but it's going to be easy to build up these things, okay? When a thing is built, of course, we will recover that P mu is, in some sense, P mu, the one I wanted to write, P mu related with these spinors. Okay, we'll come back to of course, the amplitude as we understand.